Okay, what we decided when moving from position 2 to position 1, that in position 2, VC of 0 minus equaled VC of 0 plus equaled 0 volts. This is about where we were at. And in my T equals 0 plus circuit, I had a voltage source, 240 volts. I had a 6K ohm resistor, and I had a capacitor charged with 0 volts across it. And I was writing a KCL equation. So KCL tells us the sum of the voltages around the loop equals 0. So I already defined my polarities looking like this. So going from, I'm going to go around the loop clockwise, starting with the voltage source. I'm going from minus to plus, so that is an increase in voltage. That's 240. Across the 6K ohm resistor, I don't know what the resistance is, but it's a drop in voltage because I'm going from plus to minus. So minus VR. And then across the capacitor, I'm going from plus to minus, so it's minus 0. If I wrote plus 0, it probably wouldn't matter. So I get VR is 240 volts. All the voltage is being dropped across the resistor. So the initial current would have been 240 volts divided by 6K, which is 40 milliamps, something like that. Doesn't really matter. Okay. So what's going to happen with time? I got 240 volts across this resistor. So I'm going to have a significant amount of current. Now this is bothering me. 240 divided by 6,000. Yeah, 40 milliamps. I'm going to have 40 milliamps flowing through that resistor. It's acting as a current limiting resistor. So I've had a sudden change in current. Initially, there was no current trying to go through the capacitor. Now there is. That current is going to charge up that capacitor. And as it charges up the capacitor, this voltage is going to increase. And when this voltage increases, the voltage across the resistor is going to have to decrease because the sum of the two is always going to have to be 240 volts. So the only way I can get the voltage across the resistor down is to decrease the current value. Eventually, the current is going to move to 0. We get in that DC steady state at T equals infinity. I have a 240 volt source. My capacitor is now an open circuit because everything has stabilized, and I have 240 volts across the capacitor. So we're going to start out at T equals 0. If I want to plot this at T equals 0, you're going to go from 0, and this is V, and this is 240 volts. I'm going to start out at 0, and sometime later, probably less than infinity, I'm going to exponentially go up to 240 volts and stay there. That's the most voltage I can get out of that circuit. I don't know how fast it's going to happen yet, but we'll get to there in a second. Pretty soon. Okay.
I had a little lag, but you were saying that on the last slide, over time when the current's going through the resistor.
Okay.
Going through the 6K resistor, you said that the voltage is going to drop. Meanwhile, the capacitor's voltage is going to go up.
Right.
Okay. All right.
The sum of VR and VC is always going to be 240 volts. But as the capacitor voltage charges up, the voltage across the resistor is going to have to drop then. And that's going to drop the current, and which is going to just, it's going to keep on going in a loop.
Okay, thank you.
Okay, good question. Okay, so this is what we know so far. It's exponentially increasing right after the voltage starts exponentially increasing right after I move from 2 to 1. So this is going from 2 to 1. If I do that, the voltage will increase. If I move it from 1 to 2, the voltage is going to decrease. What happens to the current is you get these current spikes in there. It starts out at 0 in this case, and then suddenly spikes up to a high value, and then decays away. And down here, it will spike up to a negative value and then decay away. Now, one thing you can notice from this graph, we haven't gotten there yet, but if you look at this, this looks like it's going way slower than here. And why are they different? Part of the reason is the rate of charging that's going on. Remember, the charge on the capacitor is going to accumulate based upon what the current is, because the current is the rate of flow of charge. So if I have higher current, I can charge it faster. And I'm going to have higher current if I have a smaller resistance. This was 12 ohms. This is 6K. So that 12 ohm resistor is going to give you more current. And when we went from 1 to 2, we had a smaller resistor, R. And so we have higher current. And if we have higher current, we're going to discharge faster. Now, people went through and studied this and tried to figure out what was going on. And what they found was the rate of decay. These are both exponential functions, but it's going to be proportional to e to the minus t, t's time, over something called tau. And tau is a time constant. And for these RC circuits, time constant is always RC. That's like an equation I had etched on my eyeballs even when I was a working engineer and didn't use equations. It's how fast things happen. So this slower circuit is going to have a tau is going to be longer. And this has a shorter tau. So moving from 2 to 1, if I look at the 0 plus circuit, see 2 to 1, moving into position 1. Yeah. Moving into position 1. I've taught this class so many times, I know where I'm going and I just make it up. I see a circuit that looks like this, and this was like 20 microfarads or whatever it was. Where are we at? We're on number 18. I don't remember how big the capacitor is. It doesn't really matter at this point. What we're going to see is my tau, and this was 2 to 1. 2 to 1. My tau equals 6,000 times C. Moving from 1 to 2, my circuit looks like this. And this is 12 ohms. The equivalent resistance that the capacitance sees is 12 ohms. So now my tau is 12C. So this is going to discharge significantly slower because of the 6,000, and this is going to discharge significantly faster. When you're calculating time constants, so this is homework too, it's on homework too. One of the things you have to find out is it's RC, but which R and which C? There's two different R's in this circuit. It's the R for the RC time constant is the equivalent resistance that the capacitor sees when T equals 0 plus. It's after the switch moves. So you have to look at the T equals 0 plus circuit to figure out what the time constant is. Okay. This next part, I've decided over the years, isn't that useful. There's a few things in here I want to talk about. I'm just going to skim over these slides. If you want to see the details of the solutions, they are in the slide solutions posted to BB Learn, but I don't think it's worth class time doing this because I want to get to the general method. A couple of things that you can get here is the energy in the capacitor. Remember the equation from yesterday or last class. It's 1/2 CV squared. So at time t equals 0, I know the voltage, it's 5 volts. My energy would be 1/2 times 10 nanofarads, which is 10 times 10 to the minus 9th. V squared is 5 squared, 25. When I multiply that out, oh thank goodness, I'm so much more organized this semester. When I multiply that out, I get 125 nanojoules. Energy is always in units of joules. Mechanical engineers never miss that. Well, you guys do. The current, well, I want to figure out what the currents are. Well, I know the voltage across the capacitor. It was 5 volts. Those two are in parallel. So I jump to the resistor. It also has 5 volts across it. Its current is going to be 5 over whatever R is. 10. Half an amp. Okay. That's all I want to say about that because I got more important things to talk about. Right. The solution to these, well, I don't even want to talk about this one. We talked about this one. Oh, there is something here I do want to talk about. 5 tau, it's over. It's a number engineers use all the time. We just say, okay, what's the time constant? What's 5 tau? That's when it's settled. That's not really true. 5 tau is how long it takes. If I put this on a graph and called this 5 tau, it would be how long it took to get down to 1% or 0.01 of the initial voltage. So it's settling within 1% of the initial voltage. Pretty much done. But if you're dealing with precision circuits, sometimes you have to go to 10 tau, sometimes you have to go to 100 tau, depending upon how precise you want to be. It's a matter of precision. Most people, when you're doing things in general, it's 1%. And so they use that. The form of the equation for an exponential decay looks like this. I'm going to give you a more general form in a couple of minutes, and we'll put the method to my madness here. It's the initial voltage times this decaying exponential e to the minus t over tau. Okay. One more thing I want to talk about before I get into my general method. The different time constants. Now, A settles a lot faster, and that actually means I have a shorter time constant because it's going to take roughly 5 time constants to settle. So this is settling in 2.5 seconds. It's getting down to 1%. This is A. Things that have longer time constants are going to take longer to settle. If you want something to settle faster, you decrease the resistance or you decrease the capacitance. You have to decrease the time constant, so you have to decrease R or C. Now, when we take ohms, let's do a little dimensional analysis here. When we take ohms and we multiply it by farads, the units are actually seconds. It's through the great magic of dimensional analysis. And I used to sit in my dorm room and figure out things like that. I would take ohms down to kilograms meters per second. I take farads down to kilograms meters per second. And I would prove to myself that it actually does come out to be seconds. You can do that if you want to, but I'm not going to do it, class. I was a units nerd, thanks to my dad. He was a physics professor. He was teaching college physics when he was a sophomore. And I don't want to do this one because it's not general enough for me. What I want to get to, oh, here's another important thing. For inductive circuits, if I just have an L and an R in the circuit, put a star next to this one. The time constant is L over R. That is amazingly also going to come out to be in seconds. Okay. And when I write the equation, it's exponential, still has this, the exponential still has the same form, e to the minus t over tau times the initial current. Okay. What I really want to talk about, yeah, they'll get used to this. I inherited these slides from somebody. She had all these educational theory words in there that she would use to test people on, which I thought was really amusing. But I started just writing smart alecky things in here, or sometimes I take them seriously. But this is one to take seriously, metacognition. You need to think about how you learn best, how you think best, and what's working for you and what's not working for you. And all those things will help you become a better student. I am a much better student now than I was when I was in high school. When I'm a better student in college than I was in high school. I was a better student in grad school than I was in high school. Last time I went to grad school, I had a 4.0. That's never happened before in my life. At one point, I nearly flunked out of college, so there's hope for everyone. I don't want to do that one either. That's not where I wanted to go. Oh, I'm going to talk about singularity functions, and then we'll talk about the generalized form. I've got enough time to do this. Okay, when we get to Laplace transforms, we'll review these again, but there's a few functions that get used commonly. And you can look at these and kind of see, oh yeah, I understand why these would be useful in electronic circuits. I've got this thing called a step function. This is like I've just thrown a switch. I've thrown a switch that was, I pushed the power button, I turned on a 1-volt voltage source. This is what this is modeling. It's called a step function, and it is mathematically called U of t. Now U of t equals 0 at time t less than 0. It equals 1 at time t greater than 0. And in between, it's kind of undefined. It's switching. So that one is fairly useful. Another one, let's say I'm switching something on and it's taking a while to power up. So the power is ramping up. This is called a unit ramp function. and we mathematically call it R of t. And it's called a ramp function. Before t equals 0, it's 0. And mathematically, if t is greater than 0, R of t equals t. So this looks, the mathematician would draw it something like this. It's 0 for t less than 0. It is t for t greater than 0. And the discontinuity, it's at 0, it's 0, so it doesn't really matter. Okay. Then we have this other crazy looking thing here. The delta function. Communications people love this. When you take EE280, the delta function is their favorite function. I don't understand those people. Okay. Basically, it looks like this. It's 0 if t is less than 0. It is infinity if t equals 0, and it's 0 if t is greater than 0. Then I laugh at them. I go, how do I build this thing? I'm someone who has to build everything. What this is modeling in a system, if you think about it, you have a sudden impulse. You've got a power grid, and somebody's just hit one of your phone poles, and the line has shorted immediately to ground. You will get something that looks like this. It won't go to infinity, but you'll get a very large spike on your system. And this is the kinds of things this is unit impulse function is modeling, but it's not a circuit that you can necessarily build. But there are three of the favorite functions to use with Laplace transforms because they make some of the equations simpler, unfortunately, so we do use them all the time.
Is that a double T just right above the ramp graph?
That is, it equals t if t is greater than 0.
Oh, okay.
You can write it mathematically correctly if you want to, but yeah, that's my attempt to do. This is why I never became a math major. I hate writing things in the right form. Okay, we'll come back to this. So here we go. I'll go through this a little bit better this time. U of t, mathematically, you get this little equal sign in the brackets. A is that it's going to equal 0 for t less than 0, and it equals 1 if t is greater than 0. That's a little bit neater. And we call it a unit step function because it goes up to a value of 1. Now, if I wanted to turn on my power supply and have it be at 5 volts at t greater than 0, I could do this, and that would equal 5 u of t. U of t. Okay, that might be one thing I want to do. Maybe I want to turn on my power supply at, instead of 0 seconds, I want something that goes like this, goes 0 to 3 at t equals 3 nanoseconds. I could write a function for that too. And the way I would do that is it would be, this is part E. It would be eraser. This is going to get me into trouble. This is when my thing freezes up. It would be 3 times u of t plus 3 nanoseconds. Minus. Minus. So if I want something that switches on at 3 nanoseconds, I need to have my 0 transition at 3 nanoseconds. If I plug in t equals 3 nanoseconds, I get 3 nanoseconds minus 3 nanoseconds, which is 0, and my transition would occur right at 3 nanoseconds. If I wanted it to go from 1 to 2, at minus 3 nanoseconds. Well, what I could do is I could put a DC source in there that's just 1, and I could add it to a step function that goes from 1 to 2, so that's just a change of 1. So that would be U of t. And the number I would have to subtract off would be negative 3 seconds. So it'd be t plus 3 nanoseconds. Okay, I can write any form of something that switches suddenly using this unit step function. And we will use that more so later in the course. Occasionally it shows up in some of these first and second order circuits though. The impulse function I'm not going to use until we get to Laplace transforms. I'm just going to skip it from now other than to write this a little bit more neatly. There goes my phone. This is 0 for t less than 0. It is infinity at t equals 0, and you can cogitate the infinite meaning of that. And it's 0 if t is greater than 0. So it's just a sudden spike on my system. Okay. The ramp function, again, we will use more when we get to Laplace transforms. These slides will come up again, and I'll talk about it more then. The most important one to understand now is that unit step function. R of t is 0 if t, we'll say t less than or equal to 0. It doesn't matter where I put the equal to sign on there. And it's t if t is greater than or equal to 0. That's where the double T came from. Okay, bit of an aside. Now we want to get into what I really want to talk about, because this is the handy dandy magic equation that will make all these first order circuits much simpler. There's a method to this. We follow the method, it's usually not that bad. Now, we've got 4 equivalent circuits that we could potentially draw. Let's look at this. The circuit, it's been sitting there for a long time. It's been sitting there since t equals infinity, we pretend like. And we're looking at the little nanoparticle, nanosecond, femtosecond right before it switches. It's steady state at that point. And when it's in steady state, we're doing a DC equivalent circuit. So all the capacitors are going to be open, all the inductors are going to be shorts. It's the easiest thing I can do to simplify the circuit. The most important thing you can do there is draw the circuit and find either VC of 0 minus or IL of 0 minus, depending upon if there's an inductor or a capacitor in the circuit. I can use that value, the initial condition on the capacitor or the inductor, in the little picofemtosecond after the switch closes. So this is, we want to do this. The first thing you want to do is draw the circuit. A lot of times on my exams, I will put a problem on there and I just ask you to draw the 4 circuits and not even solve for anything. Because being able to draw the circuits is what's going to simplify things to make it possible for you to do this. Next thing that happens is some event occurs instantaneously at t equals 0 seconds, and it causes a disruption in the voltages and currents. The thing that we know, since we've already solved for VC of 0 minus, we know VC of 0 plus. Since we may have already solved for the inductor current at 0 minus, we know the current at 0 plus. We can solve for the unknowns at 0 plus. Again, you have to draw the circuit. I wrote this too. I can use that circuit, I can use the 0 plus circuit to figure out the time constant. The important thing, yeah, the time constant, tau. What I need to do is I need to find the REQ that the capacitor.
بيقولون لك يعني هم بيقولون لك ما هو بحضوري ما هو بإجباري
I can't understand you.
وتاريخ البدء بيقولون لك هذا كله موجود ما عندهم هم حركات سعودية.
Okay, thank you. Sorry to mute them. So you find the equivalent resistance that that circuit sees at 0 plus. You use that to find tau. Tau is either RC or it's L over R, depending upon whether you have an RC or an RL circuit. Oh, hey, well, I'm in class, hold on. We will go through a couple of examples after this. The next thing that happens is you get to time t equals infinity, everything's settled out. You need to find VC of infinity, or you need to find the current through the inductor at infinity, one or the other. And once I know, this one gave me, with this step here, it gave me VC of 0 plus, or it gave me IL of 0 plus. This step here gave me tau. These equations work for every circuit. If I know VC of infinity, I can plug in a number there, I can plug in a number there. If I know VC is 0 plus, I can plug in a number here. If I know the time constant, I can plug in this number here, and now I have an equation as a function of time. You're on camera. That's my friend Pam. I can do the same thing with a current. Find I of infinity, I of 0 plus, and tau, I'm done. So that's the goal of all this analysis, is to find those three numbers, plug them into the equation, and then you're done. Yay. So we did this for the, yeah, go ahead.
Can you go back just for a quick second?
Sure.
Thank you.
Okay. We figured out what those numbers were. There was method to this madness. We knew V of 0 plus was just our voltage supply. We found out when moving from 1 to 2 that V of infinity was 0, and the time constant was R2C. So we could write an equation for V of t for that event. It's V of infinity, which is 0, plus Vs, which was 240, minus 0, all times e to the minus t over tau, and tau was R2C, and we had values for that. So I simplify that a little bit. I get 240 e to the minus t over R2C, whatever that number was, and that will have units of volts. It's as simple as figuring out those three numbers and plugging them into the equation. Okay, when we're moving from 2 to 1, if I plug in, I've got V of 0 plus, I've got V of infinity, and I've got tau. When we plug that into the equation, we get V of t. V of infinity is Vs. V equals Vs plus 0 minus Vs times e to the minus t over R1C. So if I simplify that a little bit, what I'm going to get is Vs minus Vs, or I could just do this, e to the minus t over tau. it will be in volts. Or I could factor out that VS and make it VS times 1 minus E to the minus T over tau. And it has units of volts. Okay, there we go. What are we going to do now? Here is an RC example. I will do this and I will do an RL example. We can pretty much wrap up the day. We've got to draw the 4 circuits. We're going to start out drawing the T equals 0 minus circuit. At 0 minus, we're in position A. So I've got 24 volts. I've got 3K. I've got 5K. I've got a capacitor that's open. And everything on the right-hand side is dangling because it's open. What we want to solve for, remember the key thing we're looking for is VC of 0 minus. I can do that with a voltage divider. VC of 0 minus, since it's in parallel with the 5K ohm resistor, is going to equal the same thing as the voltage across the 5K. So VC of 0 minus equals 24 times the resistor I want the voltage across, 5K, over the sum of the two, which is 3K plus 5K is 8K. So I get 5/8 of 24. I'm on part A, do. I get the number, oh, that's 10 feet. I get 15 volts. All right. We got the first bit for this formula. Now I'm going to look at the T equals 0 plus circuit. Well, at 0 plus, suddenly the switch flips over into this position. Now I've got a 30 volt source. 30 volt. I've got 4K, and I've got, it's pizza night. It doesn't exactly mean pizza nuts by pizza night. And I've got a capacitor that's acting like a capacitor. Okay. I want to figure out how fast it's going to be charging from that circuit. I know the initial voltage is on there on 15 volts. What I do, and this is where I use Thevenin, the only point in my life where I ever liked Thevenin. If I want to find the equivalent resistance that that capacitor sees, what I have to do is deactivate all the sources. DC voltage source, when I deactivate, this is an important thing to write down. I think this is the first time I said this. When I deactivate a source, but you should know this from 188, a DC source, the voltage sources go to shorts. No, open, short. I'll get it right in a minute. It's been a while since I've done this, like last semester. The current sources are going to go to opens. So for the Thevenin equivalent, I deactivate any sources that are in there because I don't know the resistance looking into the source. So what I need to do is find REQ looking into a 4K ohm resistor, a shorted out voltage source, and the REQ is now 4K. You'll need to do that like on the homework. So that's my REQ. So my time constant is REQC, which is 4K. What's it, half a millifarad, which should be 2 seconds. So we got this number here. Now all we have to do is find V of infinity. And to do that, I'm going to draw the time t equals infinity circuit. And I need some space to do that. I'm going to erase this. I miss my whiteboard. I miss the real world. I start doing crazy things like having, okay, so we'll change the color just so nothing gets blurred out. Let's make it something really different. Orange, red. Okay, so now at t equals infinity, I got to draw the circuit. It's still in position B, but now the capacitor's been sitting there a long time. It's open. I have a 4 kilo resistor, and I've got a 30 volt source. So now, no path for current to flow, so all the voltage has to be across that gap. I've got 30 volts. That is VC of infinity. I've got this one. I've got everything I need to plug into the formula. When I do that, V of t is going to equal V of infinity is 30 plus V of 0 plus was 15 minus 30 e to the minus t over 2, and it's in volts. Simplify that again a little bit. I get 30 minus 15 e to the minus t over 2 volts. We could graph that. We could graph that. It's going to, this is time t, 0, I'll just call this 5 tau, which in this case is 10 seconds. At time t equals 0, it was at 15 volts. At time t equals infinity, it's at 30 volts. Yeah. And it's going to be behaving exponentially in between there. So it's going to look something like that. That's what the graph will look like. Okay, that is an RC circuit. I think I have enough time for my RL circuit. Oh, and it ran about spark plugs. Okay, so we did that. Now we're going to look at this is the first time we've looked at an RL circuit, but we're going to apply the general method. No more guesswork, you just do it systematically. If you do it systematically, you can get through these problems. First thing I want to do is draw the t equals 0 minus circuit. Let's see what happens. This switch is going to open at t equals 0, so it's initially closed. If it's closed, I have a short circuit across that resistor. So it's basically all the current's going to flow through here. None of the current's going to flow through there, so I can just kind of ignore it. It's been sitting there for a long time. Inductor follows its DC model. It's a short circuit. So here's the circuit that I see. Being able to draw these circuits is a whole nother thing. 10 ohms, and I see a short for the inductor, but it still has current going through it. There's my circuit. My current has a choice of going, it's a current divider, but it has a choice of going through a 10 ohm resistor or a short. It's all going to go through the short. And you could do the current divider equation, but it will come out to be 9 amps. That is my IL 0 minus, which will equal IL 0 plus. Because the energy in an inductor is stored in a magnetic field. The magnetic field is what's producing the current, according to Gauss's law. So the current's going to stay constant, cannot change instantaneously. We figured out this piece of the equation. We got that from the T equals 0 minus circuit. Now I want to go to 0 plus. 0 plus is going to help me find the time constant. And this is going to help me find tau. So T equals 0 plus. I'm proud of myself. I only crashed my computer once today. T equals 0 plus. This switch is open. So now I'm no longer bypassing that resistor. I've got a 9 amp source. I still have my 10 ohm resistor. I have a inductor that's inducting, and I have a 5 ohm resistor in series with it. Now the thing I want to find out from this circuit, remember, is the time constant. And the time, so I'm not going to even try to solve it. Tau equals L over R. I need to find the equivalent resistance that the inductor sees. Remember in the last slide, I said if I deactivate a current source, it becomes an open circuit. So my REQ circuit is going to look like this. I take the inductor out, just like I did with Thevenin back in 188. Don't you wish you had a better 188, or you paid more attention to 188 about this time? I have something that looks like this. And I need to find the REQ looking into there. And a lot of people freak out at this point. They're trying to figure out, are they in series or are they in parallel? The way I figure this out is I say, I'm an electron and I'm moving through the circuit. Do I have, if I'm going through the 5 ohm and I have to go through the 10 ohm to return, they're in series. If I have a choice of going through the 5 ohm or 10 ohm, they're in parallel. So in this case, they're in series, so I can just add them together. So my REQ is 15 ohms. So my tau is, what was the inductor? 1.5 henries, 1.5 over 15 should come out to be 0.1. So important things I found so far. I found IL of 0 plus is 9 amps, and I found up here, and I found tau is 0.1 second. Okay, now I have to go to T equals infinity. Don't get over anxious with the pen or you crash your computer, Julie. Okay, haven't crashed it yet. Aren't you proud of me? Let's go with something green. Okay, so now I'm going to look at the T. Oh, just not showing up. I need to darken color. Blue. So
Did you skip 3 because it's not part of the equation?
yeah, I don't actually ever use that one.
Okay.
I don't need it. I could use it if I could ask you questions about it, but I usually don't because I'm usually, why is this so, my pen's not right. I'm just going to go back to black. T equals infinity. Okay, and we'll put a boxer. Put a box around this. Okay, so at T equals infinity, I can get the third part of this equation that I need. I only need one more thing. That's why I skipped it. This is the last remaining thing I need. T equals infinity. My whatchamacallit, my switch is open. It's been sitting there a long time. So my inductors are short. Uh-oh, I'm gonna have to do circuit analysis. The circuit analysis gets easier in this class. The math gets more harder. My inductors are short, but it still has a current flowing through it. So there's IL of infinity to remind me of that. My switch is open, so I've got the 5 ohm in there. Oh, this isn't so terribly bad. What I have to do here to find the current through the inductor is I have to go back to that current divider rule. And that's part of the reason why I reviewed it yesterday. It's part of the reason why I'm having you do the homework to review 188 and do the prereq exam to review 188. It's because I use those current dividers and voltage dividers, equivalent resistance a lot. And you'll be, that's what you needed to learn from 188, unless you're a power person. Then you have to learn, then you would have had to know the power nonsense too. If power nonsense is useful, but just not learn. Okay, so we want to find IL of infinity. It's going to be, current divider rule says it's the input current times the opposite resistor that from the one I want the current through. So the 10 ohm goes on the top over the sum of the two, 10 plus 5, and I'm on number 7, so I don't have to do the math. I have it written down. That comes out to be 6 amps. So that was the third thing I needed to find. Then I can just plug it into this equation. So the current through the inductor as a function of time equals the infinity value, which is 6, plus I of 0 plus, which was 9, minus I of infinity, which is 6, times e to the minus t over 0.1 seconds. So then this is in units of amps. IL of t, clean it up a little bit, 6 plus 3, and the exponential is only multiplied by the 3. E to the minus, and t over 0.1, that would be 10t. I could simplify that a little bit too. Amps. There's the answer. But the way you get there, you have to draw those circuits, figure out those 3 numbers, and plug them into the formula. Fairly useful circuits. We use RC circuits to charge things up to create a big current spike. And we use somebody's chatting, but I'll come to that at the end of class. We use RL circuits to create a large voltage spike. Now here's an application right here. I want to spark a spark plug on my car. So what I do is I initially have this switch closed. Let's do this qualitatively, and then I'll let you guys go. We have this switch closed. Current, this limits the current. We have current flowing through an inductor. And the current's going to reach a steady state. The next thing that happens is I throw that switch open. This is dangling. So it no longer has any current going through it. There's only one place for the current to flow, and that's into this open air gap. Turns out air, if you get it up to about 3 kilovolts, will conduct. It will break down and spark and conduct. So the current, since it has it's forced current coming from an energy source, it has no place to go. The voltage is going to rise up high enough to bridge that air gap and cause it to spark. The spark across the air gap is what ignites the gasoline in your piston, which makes the gas expand, which makes it move, which turns the wheels on your car. So that's a good application of these RL circuits. Relays is another one, but I'm out of time. I'll call roll one more time and then I will let you guys go. And I will go. I've got a couple more friends coming over and we're gonna have dinner. So anyways, Mubarak, are you here? Yes, I see you. I'm just calling your name if you're absent. Alex.
Yes, I'm here.
Okay, good. I got you. Alex Anderson.
I'm here.
Yay. Abdul Rahman Aziz.
Yeah.
Okay. You share a name with one of my favorite Kuwaitis. Lane he's graduated. Lane Dempsey. Are you here? Okay, good. Andrew Hasquit. Elena.
Oh, I'm here. Sorry. Just trying to
Okay,
unmute it.
Andrew. No, you're not Elena. Austin Lynette.
I am here, Austin.
Okay. Jordan Ramirez.
I'm here.
Okay, I assume that's Jordan.
Yeah.
Peter Schoen
Yeah, I'm here.
and Zach Schreiner.
Yeah, I'm here.
Okay, so the only person I have absent is Elena. Okay, thank you. I will see you guys on Monday. No, I won't. I'll see you on Wednesday. Monday's a holiday. Don't come to class. It won't be any fun. Okay, I will see you guys.
I have a quick question.
Sure.
On when we're finding IL or IL of 0 plus,
Right.
you got rid of the inductor. Is it because it's not doing anything since?
That wasn't in the 0 plus circuit. The inductor should be in there.
Okay.
The place where I get rid of the inductor is the 0 minus because it's been sitting there a long time. I can also short out the inductor in the T equals infinity because it's been sitting there a long time.
Okay, so if it's sitting there for a long time, the inductor gets shorted out.
Yes.
Or okay, perfect.
Yeah.
Thank you.
Okay, no problem. Okay. All right, everybody's leaving. I'm going to. I got food to eat. I'll see you guys.